Hello everyone, welcome back to another Watch Me Do Math video. In today's video I wanted to go over this step question, which is the very first step question on the STEP database. It's question 1 from the STEP 1987 specimen paper for the step 1 exam, and let's get into it. So you see the question before you. The real numbers x and y satisfy the equation 4x squared plus 16xy plus y squared plus 24x equals 0. Prove that either x is less than 0 or x is greater than 2 over 5, and similarly find restrictions on the values of y. So first things first, this exam is created by the University of Cambridge, or Cambridge admissions examinations, sort of the board run by the university. It's not my intellectual property, and I consider this fair use because it's comment upon the questions. I'm explaining how to do them to an audience. So think of it this way. When you see this question, what it is asking you to find is a set of restrictions, and from the equation itself is kind of one restriction. You know that they have to satisfy that equation. And the other restriction implied in the question is the fact that x and y are real numbers. The sort of logical jump that you need to make is to realize that because x and y are related together in this sort of quadratic system, and we know that in some cases a quadratic equation can cause the unknown within it to be imaginary or complex rather than real. The restrictions on a quadratic equation which force the unknown to be real must be the same sorts of restrictions that apply to this equation if you want to force either x or y to be real. So let's try and frame this equation that they've given us as a kind of quadratic equation, so that we can see sort of a quadratic equation with unknown x in terms of y, and a quadratic equation in terms of y with unknown x, to see where we can work from there. So let's first do that rearrangement. Let me check what my writing is like at the moment. It's a bit thick. So we have 4x squared plus 16xy plus y squared plus 24x is 0. 4x squared plus 16xy plus 24y squared. Oh wait, no, not 24y squared. Plus y squared plus 24x is equal to 0. And to rearrange that first into a quadratic equation in terms of x, we get 4x squared plus, well, these two terms are in terms of x. So if we take the x out, we get 16y plus 24 times x. And then finally, there's no constant term on this side, but there is a constant term on this side, which is just y squared because it's independent of x. So the a, b, and c of this quadratic equation, the coefficients, are sort of 4, 16, 1 plus 24, and y squared, and they're equal to 0. And if x is to be real, as is stipulated in the question, then some restrictions are imposed on the coefficients, right? Just how in a normal quadratic equation, you would expect the discriminant to be greater than 0, sort of the discriminant being the term b squared minus 4ac in the quadratic equation, which goes into the square root. You'd expect that to be greater than 0, such that the roots of the quadratic equation are not complex. X is not x is a real number because the square root does not have a negative input. And so if we apply that restriction to our three coefficients that we have here, we will find that some expression in y, the discriminant, needs to be greater than 0, and that's likely to be a quadratic expression from what we've got going on here. And if that is the case, only some values of y are allowed. So we've kind of skipped a step here. We haven't gone just for showing the restriction on x first, but we've gone straight to finding the restrictions on the values of y. But this is essentially because I've just told you the principle of doing the question. This is not particularly about how to see it, because that's something that comes with practice, but it's just letting you know what the question is all about. So if you do this calculation, b squared minus 4ac is equal to 0, which is, or it needs to be greater than or equal to 0, which is the condition in a quadratic equation for the roots to be real. And we know that b is 16y plus 24x. 16y plus 24. Oh wait, 16y plus 24 squared minus 4ac. So a is 4 and c is y squared. So 4 y squared must be greater than or equal to 0. And what's something I notice here? In fact, I noticed that this is minus 4y squared and 16y plus 24 squared. These two must be greater than 0 because this is a difference between two squares. We can actually factorize this to make our calculation a lot easier. So if a is 16y plus 24 and b is 4y, a squared minus b squared being equal to a plus b times a minus b lets us say that in this inequality, 16y plus 24 plus 4y times 16y plus 24 minus 4y must be greater than 0. Or in other words, 20y plus 24 times 16y plus 24 minus 4y, 12y plus 24 must be greater than or equal to 0. And dividing both sides by some factors that I see in common in all the terms within each of these two bracketed expressions, dividing by 4 here, we get 5y plus 6, and dividing by 12 here, we get y plus 2. And dividing by 4 and then by 12, this side gives us 0 once again. So we find the restriction 5y plus 6 times y plus 2 must be greater than or equal to 0. If we were to plot the graph of fy equals 5y plus 6 times y plus 2 against y, we'd find the two roots at y equals negative 2, and, well, 5y plus 6 equals 0 is the other root, so y equals minus 6 over 5. And because these two multiply out to form a quadratic expression in y with a positive first coefficient, 5y squared, if you multiply the two y to the power of 1 terms, this is a positive facing quadratic graph, and it'll look something like this. So if this expression is to be greater than or equal to 0, then you would start here and here at the roots of the equation, so that you ultimately find the restriction y must be greater than or equal to minus 6 over 5, or y must be less than or equal to minus 2. And that's your restriction in terms of y, and that's sort of half of the first part of this question. Really, I think this question is two parts. It's not really one distinct question, because I personally can't see how the parts A and B are related, or parts I and II are related, but if anyone could fill me in on that, I'd greatly appreciate it, because doing these questions is a learning experience for me as well. I've not even done the whole of the first step paper on the database, and I feel like I'm learning a lot for each question I do. So this process, this process can be repeated for taking this expression as a quadratic equation with unknown y with coefficients in terms of x. So if we were to write that out, we would get, taking y squared as the first bit, y squared, and then y is the This is the only term that contains a y to the power of 1, so y squared plus 16x, that's our coefficient b, times y, plus 4x squared plus 24x, which is our essentially constant factor, is equal to 0. And just like before, we expect the discriminant of this quadratic equation to be 0, so we get b squared minus 4ac equals 0, or 16x squared minus 4 times 1 times 4x squared plus 24x is equal to 0, or in other words, 256x squared minus 16x squared plus 96x is equal to 0. If we divide all of these terms by 16, or not really equal to 0, it needs to be greater than or equal to 0. If we divide all of these terms by 16, we get 16x squared minus x squared plus 6x is greater than or equal to 0, or 15x squared plus 6x is greater than or equal to 0. Dividing the terms by 3 again to simplify the expression, and remember that 0 divided by any constant factor is still 0, so that makes working with inequalities a lot easier if you try and get them in a form where there's 0 on one side. 5x squared plus 2x must be greater than or equal to 0, or x times 5x plus 2 must be greater than or equal to 0. Similarly to last time, if we sketch out the graph of fx equals x times 5x plus 2, x on this horizontal axis, we find that it's a quadratic expression, or a quadratic equation, quadratic function, sorry, I'm really mangling my words here, where one root is at 0, as if this x were 0, and one root is as if 5x plus 2 were 0, at x equals minus 2 over 5. And again, because 5x multiplied by x, the two x to the power of 1 terms in the two linear factors, multiply out to a positive coefficiented 5x squared. It's an upwards pointing quadratic graph. And so if we want this graph of fx to be greater than 0, or rather above the horizontal axis in this case, because this is our graph, this is where fx is being plotted, we just want x to be here or beyond, and here or beyond. Essentially, stating that from graph inspection, x must be greater than 0, or x must be less than or equal to minus 2 over 5, which is the set of conditions the question has asked us to demonstrate. Hold on a second. Yep, I realize what's happened here. There should be a minus. So if 5x minus 2, the linear factor, was 0, then this would be the second root. The graph would look something like this, and you'd expect x to be less than or equal to 0, and greater than or equal to the next root, positive 2 over 5. Ultimately proving the restriction that the question suggested in the first place. So fundamentally, what you are doing in part 1 of this step question is taking some restrictions that are implicit in the question, the fact that x must be real, the fact that y must be real, and the fact that the equation in the question must be satisfied. Those three restrictions you can build a chain of logic on those restrictions to get to these new restrictions with the knowledge that you already have about the nature of the roots of a quadratic equation and how restrictions on the coefficients of a quadratic equation exist depending on what you want the root to be. So that's basically what's happening here. The next part of the question is sort of completely different, it seems like, and basically what they want you to do here is to expand that expression They want an infinite series expansion of this expression. Find the coefficient of x to the n in this expansion for this thing here. So, oh, and then they want you to state the set of values of x for which this expansion is valid. So I'm just going to pause the recording here while I clean up the workspace. Alright, so for this second part of the question, there are a few different approaches you could take. The first one is to treat this as a sort of standalone function, try and find a Cullerne series for it. But the problem with that is you need to differentiate this several times over, or an infinite number of times, so that you can find a general term for what you get when you differentiate this. And that's just, I mean, I think it is quite unlikely that you will be able to find a way to differentiate this in a generalized way because of how many times you need to use the product rule, chain rule, and so on. I think it just expands into too complicated an expression to deal with like that. And another way you could try and expand this is by finding the binomial expansion of each factor. So 9 is just 9. You binomially expand 2 minus x to the power of 2, and then you binomially expand to the power of negative 2, and then you binomially expand 1 plus x to the power of negative 1. But the problem with that is that you'll end up with one expression that looks like a plus bx squared plus cx to the 4 plus dx to the 6 plus so on and so forth. You'll have a general term for that expression. Or rather, you'll have sort of two binomial series, but when you multiply them together, each individual term is going to be the sum of a whole bunch of multiplications between the two series that might be difficult to generalize. So that leads us to a third way of trying to expand this function, which is to break it into parts that you can expand easily and then add those parts up. Because if you have 3 separate binomial series, then if you add them all together, the new coefficient of x to the n will be the sum of the 3 coefficients of x to the n of the original series. And I've kind of spoiled it for you there by saying that there are 3 series, but it's basically what you do. So you break this function into its pieces through decomposition into partial fractions, basically, which I'm going to do now for you. So decomposition through partial fractions is a method that you can look up for yourself if you're curious, and it's one in which you basically take a function that's in this form. It's some polynomial expression over another polynomial expression which has been broken into its linear factors, and you go, say this were some sum of constants over linear factors, or linear factors to a certain power. And the reason people might want to do this kind of decomposition can vary from it being easier to integrate to wanting to expand something like this, like we're about to do here. So say that 9 over 2 minus x squared times 1 plus x were equal to some constant a over 1 plus x plus some constant b over 2 minus x squared plus some constant c over 2 minus x to the power of 1. It may seem like an arbitrary choice to have this linear factor be split into 2, one with the square and one with the power of 1. But the reason that I do this is one that I'm not fully sure of, actually. So that is a gap in my understanding that I'm going to admit here, and I'll try and figure that out. Hopefully I have an answer for you the next time I come to explain something like this. So I'm sorry about that. But anyways, the method is that if you have a linear factor which is repeated multiple times in the denominator, you go from the highest power that exists back down to 1 again. So anyways, say that this function could be decomposed into these 3 partial fractions set up by the rules that you may or may not know for decomposition into partial fractions. If you expand these fractions and try to add them up, you'll find some expression in terms of a, b, and c x as coefficients to x squared, x, and 1 in the numerator over the same denominator being equal to 9 over this denominator. And that allows you to figure out, because this is 0x squared plus 0x plus 9, if each of the coefficients here are known, and each of these coefficients that we're about to find out are expressions in terms of a, b, and c, and linear expressions at that, you end up with a system of linear equations that you can solve for the values of a, b, and c. So let's just do that. A times 2 minus x squared over 1 plus x times 2 minus x squared plus b times 1 plus x over the denominator, which I'm just going to write as d for simplicity, plus c times 2 minus x to get the denominator to a power of 2 minus x squared, because really what we're doing is multiplying by 2 minus x over 2 minus x, or 1 plus x over 1 plus x as appropriate to get the denominator to be equal to d, times 2 minus x times 1 plus x over d is equal to 9 over d. Or, in other words, a 2 minus x squared plus b times 1 plus x plus c times 2 minus x times 1 plus x is equal to 9, multiplying both sides by the denominator. If we expand all the terms here, we get a times x squared minus 4x plus 4 plus b times 1 plus x plus c times, well, let's see, minus x squared minus x plus 2x, so that's really plus x, and plus 2 minus x squared plus x plus 2 is what we have here. And so if we regroup these terms into terms containing an x squared, terms containing an x, and terms containing a unit, then we find that a minus c x squared plus, what's going to be the x? Minus 4a plus b plus c, minus 4a plus b plus c, x plus, what are the constant terms? 4a, b, and c. 4a plus b plus 2c equals 9. So because there's no x squared term on this side, we know that this must be equal to 0. There's no x term on the left-hand side, so this must be equal to 0. And the constant term is 9, so this must be equal to 9. If a minus c is 0, then a is equal to c. Then this means minus 4a plus b plus a, as a is equal to c, is equal to 0. And 4a plus b plus 2a, as c is equal to a, or rather 6a plus b, is equal to 9. b minus 3a is equal to 0. If we subtract the second equation from the first, we get 9 on this side and 9a on this side, so a must be equal to 1. At the same time, this means c is equal to 1, as we have this relationship from before, and if a is 1, then 6 times 1 plus b is equal to 9, or 6 plus b is 9, b is 3. So overall, this fraction must expand out to 1 over 1 plus x, 1 over 1 plus x, plus c over 2 minus x, 1 over 2 minus x, plus b over 2 minus x squared. So 3 over 2 minus x squared. And now expanding this into infinite series is a much easier job, which is pretty awesome if you ask me. So 1 over 1 plus x is something that can be easily expanded by using the normal sort of binomial expansion that we are used to. So it would be the sum of well, I want to write n factorial, but I know that's not right. We know the coefficients. We know the coefficients are going to be 1 minus x, and then plus minus 1 minus 2 over 2 factorial x squared. So this is part 1, term 1, plus that x squared minus that x cubed, or plus that x cubed. I can see the general pattern is that it would be the magnitude of all these numbers cancels out, but it seems to alternate plus and minus signs. So this would be 1 minus x plus x squared minus x cubed, and so on. And so the x to the n coefficient of term 1 is minus 1 to the power of n, it seems. Now for 1 over 2 minus x, what I thought we might be able to do is to make this form similar to the form of the converging geometric series. Essentially, because we have the geometric series formula u1 over 1 minus r is equal to the infinite sum of u1 r to the n minus 1 from n equals 0 to infinity. This kind of looks like this, so we could express this in a form that does look like this. So dividing both the numerator and the denominator by 2, we get u1 is equal to 1 over 2, and x over 2 is the common ratio. For the expansion to be valid, well, firstly, here, for the expansion to be valid, x needs to be, the absolute value of x needs to be less than 1, because we're using the binomial series. For this, the common ratio needs to be less than 1, therefore x over 2 needs to be less than 1, x over 2 needs to be less than 1, and x needs to be less than 2. So those are two restrictions we have so far. This becomes the sum of u1, 1 over 2, r to the n minus 1, where n is 0 to infinity. And what's r? It's x over 2. Oh right, this starts at n is equal to 1. Sorry, not n is equal to 0. But I guess we could just use 0 and let this be n rather than n minus 1 for simplicity. And so if we were to take this 1 over 2 out of this bracket, we'd find that this is the sum from n equals 0 to infinity of 1 over 2 times 1 over 2 to the n times x to the n, which conveniently tells us that our x to the n coefficient of the second part is 1 over 2 to the n plus 1. So what next? We want to find the x to the n coefficient of the third part, 3 over 2 minus x squared. We already know that for part 1, it's minus 1 to the power of n. For part 2, it's 1 over 2 to the n plus 1. What about for part 3? Well, if we know that 1 over 2 minus x is equal to the sum from n equals 0 to infinity of 1 over 2 times 1 over 2 to the n times x to the n, then if we differentiated this, would we get something in the form of a to the 2 minus x squared? We would, because if we let u be 2 minus x as an application of the chain rule, then by the power rule, the power here would go from -1 to -2, and a would be 1 times -1, which is -1. So if we differentiate this side with respect to x, we get -1 over 2 minus x squared, or -1 times 2 minus x to the -2. And that would be the same as differentiating this whole series here with the same restriction that x over 2 must be less than 2, or x must be between 2 and -2, exclusive. The same restriction applies, but we can still differentiate this to get, well, the constant term at the beginning is sort of messed up. So this becomes, wait, hang on, let me think about this first. The constant term becomes nothing, so we could ignore the n equals 0 case. Therefore, this series starts at n is equal to 1. If we differentiate, we get x to the n minus 1 as our power of 0 term, and our 1 over 2 to the n plus 1 gets multiplied by n. So if we want x to the n again, we go back to n is equal to 0, and we let this be n plus 1. This becomes 2 to the n plus 2, and we have x to the n here, because we've just let the new n be the old n plus 1. Is that right? No, we've let the new n be the old n minus 1. Yeah, that's right. So the coefficient of each term is this n plus 1 over 2n plus 2 term. And that's our x to the n coefficient of the third part. So overall, if you sum up the x to the n coefficients of each of these three parts that constitute this function here, you will get the coefficient of x to the n in this expansion, which is what you're ultimately looking for. And that is minus 1 to the n plus 1 over 2 to the n plus 1 plus n plus 1 over 2 to the n plus 2. Sorry, my writing tablet isn't very good for drawing big boxes. And what about the restriction on the validity of this series? Well, if you were to graph the function, you'd see that it has an asymptote at x equals minus 2, an asymptote at x equals 1, and so you would probably end up with a function that was only valid from here to here, because the closest, like there's a thing called a radius of convergence, and when you expand a series like that, using either the binomial expansion or the what's it called, Cullerne series, or the geometric sum to infinity. When you expand functions like that, you inevitably get what is either a finite polynomial of odd degree or a finite polynomial of even degree. And if it's of odd degree, then it's rotationally symmetric about the origin with those two techniques. And if it's of even degree, then it's just straight up symmetric about the y-axis. And that means basically if there's an asymptote on one side that is 1 unit away, that's the closest asymptote, the graph will also behave asymptotically on the other side if it's an approximation of the function, because it's symmetrical, despite there not being an actual asymptote of the function located at that point. So despite the fact that the nearest asymptote is x to the minus 2, there is effectively an asymptote of x to the minus 1 in this function here, because the approximation we're making overall is just a odd or even polynomial about this point of the origin. So it's as if there were an asymptote at x equals minus 1, because this must be symmetrical in some way, like that or like that, with our approximation here up to the real asymptote at x equals 1. And I'm not sure if that was a mathematically, logically sound explanation, but it is the explanation that works for me intuitively in terms of understanding why this is the case, and hopefully it makes sense to you as well. And that's why overall we go with the most restrictive condition, which is that minus 1 must be less than x, which must be less than 1. X must be between minus 1 and 1 non-inclusive is our final condition, because it's also the most restrictive condition we started with when we were calculating the infinite series. Because this is just some extra intuition to say why that is the condition that does the restricting. But if you want to get by this question without those other mathematical bits of knowledge, then just keeping track of the restrictions you imposed in the first place in order to use infinite series formulas is helpful, and it will end you up with the same result. X must be between 1 and negative 1. Now, disclaimer, I do these step questions before I make videos about them. Like, I fully do them and I make sure I'm fairly confident in my answer. But that does not mean I'm 100% guaranteed not to have made an error in this video, or not to have led you to the wrong answer altogether. So if that is the case, please do let me know in the comments, or email me at watchmedomath@gmail.com, and I will try to respond to this quickly. And hopefully you found this video interesting, or you enjoyed it, and until next time, thank you for watching.